Hello, welcome to week 2. Today let's simplify something because at first that thing might look complex. What is that? It is a data types. But once you see the pattern, it becomes surprisingly intuitive. Most people think data science starts with fancy models. Actually, it does not. It starts with understanding what kind of data you are even looking at. And honestly, in real projects, this is where things quietly go wrong. A company spends months building dashboards, a startup trains a machine learning model, a team celebrates insights, and later they realize that they treated the wrong type of data the wrong way. Which means what? They have created wrong charts, they have calculated wrong averages, they have made wrong assumptions, and ultimately wrong decisions. But what is the scary part in it? The code still runs perfectly. That is why today's topic is one of the most underrated foundation in all of the data science. It is types of data and measurement. Now, let's see why this matters. Let's imagine a hospital data set. You have patient's age, blood pressure, disease severity, blood group, satisfaction rating. Now, I will ask you an interesting question. Should all of this be treated the same way? What do you think? The answer is not at all. Because data is not just values. Data carries meaning. And if you misunderstand that meaning, your analysis becomes mathematically correct but logically wrong. Most beginners don't notice this at first. What do they think? They think if it is a number, I can average it, but not always. For example, if I have a customer satisfaction index, which is rated 1 is equal to poor, 2 is equal to okay, 3 is equal to good, 4 is equal to excellent. Can we really say 4 is twice as good as 2? No, not exactly. So this tiny misunderstanding changes everything. So think of data like objects in a kitchen. A knife, a spoon, blender, microwave. These all are kitchen items. But we don't use them in the same way, right? So similarly, all data set contain values, but not all values behave the same way. Some data measures quantity, some labels categories, some represent rankings, some flows continuously, some only jumps in steps. And your entire analysis depends on recognizing this properly. If you remember just one thing from today's video, what you should remember? I'll tell you. Data type determines what operations are meaningful. Remember this. Data type determines what operations are meaningful. And this one idea alone can save you from dozens of future mistakes. Now let's start with biggest distinction. Numerical data. What is numerical data? It represents measurable quantities. For example, salary, temperature, height, revenue, distance, and these values have mathematical meaning. You can add them, average them, measure differences. For example, if I say one employee earns 80,000 rupees and another employee earns 10 lakh rupees a month. Now, there is a real quantitative relationship. Understood? The second type is categorical data. Now this represents labels or groups. For example, blood group, city, product, then gender, payment method. Now here is the important insight I want to share. Even if categories are represented using numbers, they may not actually be numerical. For example, if I say in my database 1 denotes to Mumbai, 2 denotes to Pune, 3 denotes to Delhi, those numbers are just labels for simplicity. Delhi is not greater than Pune, but beginners often accidentally treat encoded categories as real numbers. And suddenly the model starts learning imaginary patterns. In production systems, this causes surprisingly subtle bugs, especially in machine learning pipelines. So this is one example where you can see the encoding of data. It is just for reference, okay? But I want to give you some insights. A machine learning model does not understand meaning. What does it only do? It only sees patterns in numbers. Understand this. It only sees patterns in numbers. So if you encode categories carelessly, the model may invent relationships that do not exist in reality. And that is why feature engineering is less about coding and more about preserving meaning. Because as a data scientist, you know meaning of data. Now we will go to second part, which is ordinal versus nominal data. Okay. Now let's go deeper into categorical data. Because not all categories are equal, we have nominal data where no order exists. Example, blood group, colors, countries, departments. There is no ranking. Red is not higher than blue. Simple, right? And in ordinal data, what happens? Order matters. There is an order. For example, customer satisfaction, education level, pain severity, movie rating. There is ranking, but the gaps between the values are not guaranteed to be equal. That's the subtle part. For example, the emotional difference between average and good may not equal the difference between good and excellent. And this is why blindly averaging ratings can sometimes mislead businesses. Now I'll give you one real business case. Imagine I have an e-commerce company and there I have customers rating delivery experience from 1 to 5. Now management sees average rating improved from 3.8 to 4.1. How does it sound? Good, right? But deeper analysis reveals what? Most customers moved from very bad to neutral, not good to excellent. That is a completely different business story. Do you understand now what do I mean? Now it is showing the same average. So suppose if I have a data which is improvised from very bad to neutral rating, and the second data set which is improvised from good to excellent, and in both the cases I'm seeing the same improvement, 3.8 to 4.1. Does it mean the same? No. But what is happening when I'm seeing this number? It is giving me that same kind of insight. So that is why experienced analysts always investigate data meanings before summarizing metrics. Now we will go to part 3, that is continuous versus discrete data. Now we will discuss numerical data more deeply. We have discrete data. Discrete data is countable values. For example, number of customers, defects in manufacturing, website visits, calls received. You can count them individually, usually whole numbers. You cannot have 3.7 people entering a store. Okay? And in continuous data, they are measured values. For example, height, weight, time, temperature, speed. This can exist across a continuous range. Even if measuring tool rounds them, this distinction matters enormously in statistics and machine learning because different models assume different behavior. Now, this is the example of discrete and continuous data. This is a basic example. This is the same example which I gave you for the e-commerce company, right? Now I'll give you one more example. Suppose a company analyzes employees' performance and they encode junior is equal to 1, mid-level analyst is 2, senior is 2, a senior is 3, and then they calculate averages and correlation. Now you tell me what is the problem here. The problem is those numbers represent hierarchy labels, not actual measurable distance. And the gap between junior and mid-level person is not equal to mid-level person and senior level person. But mathematically, the system is assuming that. And suddenly, what do I see? Beautiful charts, confident dashboards, completely flawed conclusions. In real projects, this is where things get tricky because most business errors don't happen from complicated AI. They happen from misunderstood data. Okay? I want to give you one more insight before moving forward. A huge portion of AI expertise is actually data understanding, not model complexity. Senior data scientists spend far more time asking, what exactly does this variable mean, than writing fancy algorithms. And that may surprise beginners. Now I have attached a link in the description for one repo reference, that is the Python Data Science Handbook, and it does something beautifully practical. It treats data structure not as abstract theory but as containers of meaning. And this mindset is incredibly important because professional data science is less about memorizing tools and more about choosing the correct representation of reality. And that is the real skill. Okay, so please go through it, and I will request you all to to learn from it. It will help you a lot because it will help you in building that real skill which many people lack. I will tell you some common mistakes which people make generally, and I want the viewers or listeners to avoid it. The mistake number one is treating encoded categories as numerical quantities. Never do it. Second, using averages on ordinal data without context. Don't do it. And third, choosing wrong visualization. For example, if I'm using histograms for categorical variable, is it correct visualization? No. Mistake number 4 I want to mention is ignoring business meaning behind the variables. Never ever do it. A dataset column is not just a column. It represents a real world process. Now, I know it is long, but I want to give you one key takeaway, and I want you to remember this one thing. Data science is not about numbers. It is about meanings. See, I have written it here. It is about meaning. So before analyzing any data set, ask these questions. Is this measurable or categorical? Is there any order in this data? Is the distance meaningful? Is this counted or measured on every column? You have to ask it. And those questions will alone instantly improve your thinking. And honestly, this is what separates dashboard creators from real data analysts. And before concluding, I want to tell you, if this made things a little clearer, I would love for you to continue the journey with me, and the resources that I have mentioned, the handbook link and this notebook link I am attaching in the description. If you would like to explore them, please do it yourself. Thank you.